Okay, yesterday I told you what the Hecke category was, or is, and I told you it was a diagrammatic algebra where you draw pictures from parts, and then you have certain relations, which are just, again, more pictures, and some of them are, well, most of them are there. And I've just put them there so I can refer to them in this talk without you having to remember anything. And then I drew my favorite one because I like this picture on the slide. And the point of this algebra is that its representation theory is governed by parts. And that is what the algebra is. So I defined what the algebra, I told you what the algebra is, but it probably didn't process. So I thought of a quote when I was awake at 4 a.m. flung over this morning, which is Morpheus from The Matrix, which is no one can tell you what the Hecke category is, you have to see it for yourself. And so today we're going to see it for ourselves. And for me, seeing something for yourself means reproving stuff you already knew in a new language. So that's what we're going to do today. And it's also going to teach us what intersection forms are. And this is going to be really important for tomorrow when we calculate these torsion-explosion counterexamples. Okay, so let's see what today's all about. So I told you that this algebra is cellular. And what that means is that you have cell modules, which are just exactly the same thing as spec modules for the symmetric group. They're just well, in the symmetric group, it would be standard tableau shape lambda. Take the basis elements from this algebra and you look at them modulo more dominant terms, which for us means terms which have fewer strands, fewer propagating strands, which is just things which are lower in the Brouillard order. Okay, what is the intersection form? It is just take one diagram, put it on top of another one, and see what you get. So you're going to get some scalar, and the scalar is just coming from this. So namely, we're going to take the diagram today. It'll look like this. That'll be CS. Yep. We're going to take another one, CT, and so I've turned this upside down. And when I take this product, I'm always going to get something. So at the top of this is an idempotent common colors. At the bottom is an idempotent common colors. And so when you rewrite this, you're just going to get, well, I'll go to this next slide, 1 lambda, the sort of skinny bit there, times some coefficients. And those coefficients are what is going to tell you about the module, essentially. These are the gram. These are going to be recorded as a gram matrix for the bilinear form, and that's going to be really important. And because I'm only doing it within the spec module itself, the cell module, the stand module itself, they're going to have the same shape, these parts, S and T. Okay, so now let's take a field. I told you that we have cell modules, standard modules, spec modules, and then they have forms of them, bilinear forms. Why do we care about these forms? Because if we take the radical of this bilinear form and quotient out by it, we get the simple one. Okay, so these spec modules give us a way of getting a handle on simple modules. And that's what cellularity is all about. And the end of last lecture, we said, but we didn't really do all this, so we didn't really say anything. We said that the p-Kazhdan Lusztig polynomials, the things we're interested in for this course, the subject of Lustig's conjecture, are simply the way we pass between these two bases of the growth integral. They're easy to construct spec modules, which we have a path basis for. So they're easy. But simples are more interesting, and we get from one to the other using the intersection forms we're going to play with today. Okay, are there any questions? Let's go then. Right. So I just told you that we're going to do that, but first I'm just going to do a little bit more motivation. We're going to compute these polynomials, these decomposition multiplicities. And of course, understanding the decomposition numbers of an algebra is the same as understanding the dimensions of the simple modules of that algebra for a cellular algebra. Yeah, I'm just going to leave that at that. And if you don't believe that, that's a cellular thing that you can look up later. Now, if computing the, if a simple is just the spect module quotiented out by its radical, well then, of course, computing the dimension of that top bit is the same as computing the dimension of the radical. Because you just do, we know the dimension of the whole module, and we minus the simple module to get this guy. Okay. Now, for infinite primes, or characteristic zero, however you want to call it, there is an algorithm for computing these Lustig polynomials, which I denote with an infinity to note that the prime is infinite. And the point of Lustig's conjecture was that for the parabolic Foster systems controlling algebraic groups, in particular for us the type A one, Lusztig said that the most important p-Kazhdan Lustig polynomials should be independent of the prime, providing the prime was bigger than n, the constant number. So if you like, all questions about representation theory, that's not quite true, important questions about representation theory can be calculated algorithmically, was the conjecture. Okay, now, it's not true. So let's talk about how we talk about the fact that this is not true. Well, we're going to say that there is prime dependence, there is p-torsion, if the dimension of this radical is different in characteristic zero over complex numbers to what it is over characteristic p. So, I mean, we said that the dimension of the radicals are the same as the dimension, well, okay, computing these is equivalent to computing the dimensions of the simples, which is equivalent to computing these. So if we find prime dependence here, then we've found Lustig polynomials, p-Lustig polynomials, which depend on the prime. They have p-torsion. Okay, so to disprove Lustig's conjecture, all we need to do is find some p-Lustig polynomial, which he said would be independent of the prime, and just find a radical, and find the radical to exhibit that it does in fact depend upon the prime. Okay, that's the strategy. Yes.
You should repeat what you said. You can make p.
Oh, just complex numbers. It's just that you can say characteristic zero. If you're old school, you'd say it's characteristic infinity, and that sort of went out of fashion. But I think it's quite nice for this because as p gets very large, this sort of does become nicer. Okay, any questions? Okay, so now we're going to compute some of these intersection forms in cases that we already know and stuff like that. So I'm going to look at some cases that do not depend upon the characteristic to show you stuff. So let's look at S2 again. Nice and easy. So we constructed the basis of this algebra yesterday. It was 5-dimensional, and it had the basis consisted of this guy, and then this is 2 squared is 4. So this one, normally you flip him, normally you put him on top of himself. That's the whole algebra. So these are the 2 cell modules, which create the whole cellular basis. Okay. I'm now going to show you how to compute the bilinear form on this guy. Okay, so all I have to do is take a diagram and put it on this twisty ground. So here, if I take that one and then flip it upside down, put it on top of it, well, it just looks like it started, right? Here, if I take this one and this one, it looks like this. That's the product. You can do this one, and finally you can do this one. So those are all the ways of multiplying these 2 diagrams together to get a 2 by 2 matrix. There you go. Now, what I didn't say yesterday, but if you've ever seen a diagram algebra or a category before, you'll probably guess this don't make no sense. So we say it's 0. So that product is 0. You can't put a bar, but if that's the image of an amp or the anyway, you can't take a product like that and just set it to be 0. So both of those guys are 0. Now, one of our relations, which you can see over there, which is that if a barbell exists to the left of a diagram, which it does here, that is also 0. Okay, and so the bilinear form here has rank 1. And notice that this doesn't depend on, there's no p. There's no p here, is there? So this is characteristic free. And lo and behold, what that tells us is that the radical of this bilinear form is one-dimensional, and the simple quotient is also one-dimensional. And as you can probably guess, this is the radical, this is the quotient. Okay. And over here, if you do this product, you just get the thing you started with. Okay. And so this guy is one-dimensional with a 0 radical. The radical is nothing. So standard module, which is simple, standard module with a radical and a simple head. There you go. Ta-da. So we now understand the Hecke category of S2. Are there any questions about the Hecke category of S2 before I just do the concluding one on the next slide? Cool.
Why do you label the second simple by 1, 2?
Because that's the transposition. So 1, 2, there are 2 elements of the symmetric group. The identity in this group 1, 2 elements, and the transposition 1, 2. Cool. Okay, that bilinear form did not depend on p. So these p-Kazhdan Lusztig polynomials are completely independent of the field. So we have that there was the standard module was simple in one case, and it had a simple one-dimensional head and a simple socle, which was in degree shift q, right? Because it had a spot. Spot is degree q, degree plus 1. Okay. And lo and behold, this is what I was saying a moment ago. If I take this 2-dimensional module, it has a simple head given by nothing, and a simple socle given by the other guy. And 2 lessons to learn. 1, it was really, really easy when we, if we took a diagram like this, and put it on top of, sorry, you're not going to be able to see that, it's in the cheat sheet somewhere. If I take a diagram where the idempotent at the bottom, and I take it with a product with something where the idempotent at the top are different, then the product was 0 because the diagram didn't make no sense. So when we do these products, we're going to get matrices with lots of zeros in, because if the top of one diagram is not the same as the bottom of the other one, the product has to be 0 because the diagram isn't making sense. So we can limit our attention to idempotent by idempotent. And there's another cheat, which is that the grading. This product has to be a scalar multiple of the idempotent. So if you don't pick diagrams of opposite degree, well, it's not homogeneous, it's a graded algebra. The only coefficient that you can have the idempotent of degree 0 in is coefficient 0. So if your algebra, if you've picked 2 diagrams which don't have total degree 0 when you take the product, it's 0. So we can cheat by saying, okay, the idempotents have to match, and we have to pick something where S and T have opposite degree. Degree of S plus degree of T must be 0. Cool. Okay, so before we carry on, any more questions on that slide, on S2?
So for recursion 0, this is like category over S2, right?
Yes.
And then what does it have a meaning over recursion?
Sure. It is the area around the Steinberg weight for the algebraic group SL2, if you like. It's a bit overwrought, but or it's modular category M, if you prefer that. So now let's do S3. So I'm going to show you how to construct the representation labeled by this guy here, one blue strand. So you can always just do a path which goes to the point. Done, okay? What else can we do? Well, if we took the path which goes blue-pink, we can fold him up to get that guy. If we take the path that goes pink-blue, we can fold him up to get this guy. If we take the path that goes pink-blue-pink, we can fold him up to get this guy. And then there's one more we can do. So we can fold up the same path again, but this time, instead of getting something of positive degree, we can fold him up by going +1, -1, and then that's at degree 0. And I claim that this is actually going to be the submodule structure for this standard module. I claim that this module has a two-dimensional head, which does not depend on the characteristic field of the field. And then it has composition factors corresponding to blue-pink, pink-blue, and blue-pink-blue in the relevant gradations. Do people understand what this picture is supposed to say? I haven't shown this yet, it's a claim, but do we understand what the claim is? Any questions?
What do you mean by the arrows?
That's if you want to call it equivalent relations, it's just depicting the submodule structure. That this is a submodule, this is a submodule, so this is a submodule, this is a two-dimensional submodule, this is a two-dimensional submodule, blah, blah, blah. You can get from here to here by multiplying an element together. Okay, let's prove it. So we claim that this diagram does not belong to the radical. In fact, it belonged to that two-dimensional simple head. Now, let's do the bilinear form and see if I'm right. Oh, and remember, over any field, so we need this to be like 0, or at least have no prime divisors. I guess which means 1. 1, right, okay. So, I've already told you that I'm allowed to idempotent cheat, right? I do not need to consider the product of this guy with the other thing, any other diagram, because, okay, I can idempotent cheat and I can grading cheat. I know that I only have to consider products where the product of the thing matches on the idempotent, and I only have to consider products where the total degree is 0. Now, there's only one other diagram with blue, pink, blue, and that is degree 2. So this product here is the only one I have to calculate to understand when this is in the simple or if it's in the radical. So let's just do the product. And now all I'm going to use is the 2-color barbell relation, which is over there on the top board in the bottom right corner. So I'm going to pull this pink barbell to the left. And okay, that is the rule that I've written up there for pulling a barbell through a color of adjacent residue. And okay, so I pulled it through, and I got this guy here, these two. Now there's another thing up there called the fork annihilation relation. So if I put that one on top of itself, these two guys are actually 0, right? Because I've got a fork on top of another fork. And this guy I can straighten out using the fork spot relation, where this all just ends up being one strand. And so this is just equal to this guy on the nose with no coefficient. And so this is completely independent of the characteristic of the field, and I was right with my claim, so I didn't fail in the talk. Yeah. So who is happy with what I've just done now? Oh, that's a happy or a question? Happy, okay. Anyone not happy, I guess, would be the way of expecting a reaction from a crowd. Oh, we have unhappiness, right? No, because you're allowed to, in Castellistic theory, pick your favorite path to a point. You're allowed to pick your favorite reduced expression, and I did that in a way that I suppressed. So, what I did just then was I showed you that there was a 4-dimensional module. So I put lambda across, so lambda here would be that blue point. And then mu here is all the idempotent which don't kill delta lambda. And so I showed you there's a 1, 2, 3, 4, 5-dimensional module where I said that these two degree 0 pieces gave you a 2-dimensional simple head, right? And what I'm going to show you now is that, okay, this is a way of thinking about something we already knew. So I told you that it had 4 composition factors, the guy at the bottom, the 2 guys there, and the guy at the top. But that the simple module was 2-dimensional. It had something in this weight space and something in this weight space. And in fact, actually, I can factorize this matrix of weight spaces by just saying, okay, every weight vector in a module must occur in some simple, and that simple must occur as a composition factor of the module. It's vacuous. It's just completely obvious. A little bit of idempotenting, all good and true. Now I can add in all the other weight spaces for you there, all the dimensions. And in fact, there's only 2 kind of interesting ones here. There's this 2-dimensional guy, this 2-dimensional guy. Everything else is sort of, you can use the idempotent tricks to understand all the other guys. But I want to factorize this matrix and tell you where every single vector lives in that module. And I can do it like this. So notice that if this 1 here, by multiplying this matrix with that one, this 1 gives me a q squared, and, sorry, 1 plus q squared, so it gives me that 1, and then multiplying here, wait, okay, 1, 0, q, that's it. So this 1, 0, q here, times that 1, gives me 1, 0, q there, and that is how this matrix factorizes. And over a field of characteristic 0, this is just how you compute the Lustig polynomials. You just compute the degrees of paths, put them in the matrix, factorize it so that you've got something which is invariant in the form of Q inverse and something which is strictly positive degree. But what I've shown you is that in fact, this entry here is 1 in any field now. So in fact, these Lustig polynomials are utterly independent of the prime. Okay, so who did not understand what that was all about? Yes.
Can you explain this matrix on the left again?
This matrix on the left.
In the previous example, what was mu?
In the previous example, I varied over all the mu's, right? So I took lambda, I took this cell module labeled by 1 blue step, just the color blue, the transposition 1, 2, like. And then I looked at every single weight, every single path that could be folded up to terminate at the point blue. And I recorded that in the matrix. And I said that in fact, the only possible guy that could be in the simple head was the one that looked like, I'm going to use my colors. Thank you, Andrew. The one that looks like this. And that vector has shape blue, weight blue, pink, blue. And so it goes in shape blue, weight blue, pink, blue. It's that entry there. Does that make sense? Any other questions? Okay, so this is a second result. We've seen that the p-Kazhdan Lusztig polynomials were independent of the prime for S2, and now we know it for S3. So we're getting to a point where we're actually like, okay, I've played with a Hecke category now, and I've actually computed some decomposition numbers, and there are ones I knew before. I already knew that SL3, or modular category O for SL3, didn't depend on the characteristic of the field, but Lustig's conjecture was true there. And now I've seen it actually in, seen it, okay? So, I'm gonna go on to the next slide now.
So if we're ordering by group, why was that? I thought the first column would be the identity.
So the first column is the longest word, and the last column is the identity. So this module, the guy labeled by the identity has the most composition vectors, whereas the guy labeled by the longest word, you can't fold up anything to terminate at the longest word except for the longest word.
So is that all of them wrote in one view is that the incarnation of like the deep projection composition series?
It is actually the biggest standard modules composition series, and that standard module is actually projective, but it's not the biggest projective because, for example, these are the projected multiplets. So if I take a projective and look at the spec multiplets that do go this way, and if I look at the standard module and look at the simple composition multiplets, do they go this way? BGG reciprocity. Okay. And let's see P. Let's see P actually matter. Okay, so I'm now going to show you SL2, the best algebraic group, the only one we understand. What does it look like? So, oh, geez. Oh, that one doesn't move, does it? Right. So SL2, it is governed by the affine symmetric group on 2 letters, modulo the finite parabolic. Okay, so we know this. We've drawn this picture before a billion times in Bolton and Harris. We know what this is about. So we start with 0, and okay, I'm going to have blue to be my first color. So the first reflection we do is we go through the blue line, right? And like so. So in Bolton and Harris, draw. Yeah, that's fine. Go. You use natural numbers to label representations of SL2. So if I take blue and pink, what do they generate? Well, it's the affine symmetric group on 2 letters. That actually, I can reflect on this side as well, can't I? But I don't want Z integers to label representations, so I just quotient out by saying anything without reflections. That's going to be my parabolic. So that's why it's S2. So affine S2 generated by blue and pink together, modulo the parabolic generated by one of these things. So that I actually label SL2 representations by natural numbers. And what I'm going to compute for you is a decomposition number. And I said I was only going to do ones that we already know. You might not know this one yourself, but it's in James's book. It is an example of a decomposition number for S12, the symmetric group on 12 letters. It's an example of the trivial representation occurring as a multiplicity in a spect module with prime depending on the prime. Of course, James doesn't talk about the Hecke algebra in his book, but the P is 3. There you go. So let's do it. There are 2 ways of getting a path of this weight and this shape. So it's got to go blue, pink, right? And it's got to, I'll draw them, why not? What you're going to do is you're going to, well, there they are, anyway. You can go blue, pink, so I didn't do the pink, and then bounce blue, and then pink. That's one of them, and the other is obtained by folding that up. But they're parts in the Bruchar graph, and they're the only 2 of that shape in that way. So I just have to calculate the intersection form, the products of these elements. And okay, I claim that it depends on the characteristic. I'm going to see p-torsion, but p is 3, I'm actually going to see something happen. So here is the matrix. So I've taken this one on top of this cell, this one on top of his cell, and this one on top of that one is this, and then that one on top of this one is this. So I just drew the pictures. 2 by 2 matrix, let's do it. So the first thing I'm going to do is I'm going to use what's called the fork-spot relation to suck these dangly bits back in and get a nice idempotent here. And I was trying to get the idempotent, so huzzah. And lo and behold, I'm just going to write, okay, it's the idempotent labeled by blue, pink, and it's occurring with scalar 1, right? So now I'm going to do these products, and hopefully I'm going to see something where I get a prime dependence. And I'm going to use the blue-pink barbell relation. And notice that on that board, it says the blue-pink barbell relation depends on the rank of the Coxeter group. Why? Because it's really just a Cartan, an entry in a Cartan matrix. So for S2, an affine S2, the Cartan entry is now going to be -2. So when I pull that barbell through, I get double, is what it says, times 2 if the rank is 1. So when I pull him through, I'm going to get 2 times the one where I break up the guy, plus the ones where there's a barbell all the way to the left, so they're 0, so I haven't depicted them, but there you go. Same thing here with a little bit more work. So, oh, okay, so -2 times the identity, -2 times the identity. And what is the rank of this matrix? It is it's a 2x2 matrix, and the only p that divides the determinant here is p is 3, right? Because I can always take the matrix. It's got an eigenvalue given by 1 minus 1 when p is 3, but no, not otherwise.
Do you mean rank 2?
Yes, rank 2 unless p is 3. So when p is 3, I'm going to get a submodule here given by a linear combination of those two diagrams. And which linear combination is it? It's actually this one. So this is L blue pink, appearing as a submodule of this two-dimensional weight space of this module here in characteristic 3. Cool.
Should say rank 2.
Oh, okay, then, I see your point, sorry, yes, rank 2, yeah, okay, rank 1 or rank 2 applies. And that is the composition factor multiplicity of this guy coming from p is 3. So, did anyone not understand this slide? Does anyone not know what's going on? This was the most complicated one, so you're allowed to not understand it, no judgment. Okay. So now let's just get the ball rolling. Let's disprove Lusztig's conjecture. So what did Lusztig conjecture? He conjectured that certain p-restricted p-Kazhdan Lusztig polynomials should be characteristic free, providing p is bigger than the rank of the Coxeter group. But we're not going to do that because affine Kazhdan Lusztig polynomials are hard. So what we're going to do is a toy model of the Lusztig's conjecture. We observe that affine Sn is made out of lots and lots of copies of finite Sn. How so? Well, here. So this is, if you imagine this tiling off to all of R2, this is the Bruhat graph of affine S3. And I've shaded in gray, but you can't see. These blue-pink, if you take these blue-pink ones, these are all copies, I mean, you can see it, right? These are lots of copies of finite S3. And in fact, for each of these finite little copies of S3, you have a subquotient of the affine Hecke category that is simply isomorphic to that the finite S3 Hecke category.
That's a question. So the Lusztig conjecture, we say p-restricted anti-spherical, that means the partitions are p-restricted?
Yes.
And what is that conjecture here?
Well, for p bigger than n, I don't know. It appears in
One
of his papers somewhere. It's a contentious issue. And so all we have to do is we need to exhibit p-torsion for one of these finite Hecke categories. And this is called looking around the Steinberg weight, because if you're interested in the algebraic group SL3, you would take a p quotient here. The first copy of the full finite symmetric group you see is around the weight p minus 1 rho, called the Steinberg weight. So if you go a little bit in any direction from this, you will get a finite copy of the symmetric group on 3 letters, and SN letters for higher. So all this slide was saying was I'm going to look at the Hecke category of a finite group. Okay, so now I'm going to use the grading trick and the idempotent trick to tell you the lambda and the mu, which will give you counterexamples to Lusztig's conjecture. So we want to use the grading trick, and we want to use the idempotent trick. So we want to look at a weight space, I've swapped between left and right by accident through this talk, so one side makes sense of this. So we're looking for a weight space where the grading only has a single element of degree 0. So we're looking for a lambda and a mu, so that this weight space is has a single degree 0 element, because that way the only product I have to consider is that degree 0 element with itself. And well, you can consider all the other products too, but if I find p-torsion in one of them, then I'm done. And I found counterexample to Lusztig's conjecture. If lambda and mu satisfy Lusztig's conjecture, and I can find, yeah, okay. I'm going to look at things like this. Why? Because 1 by 1 matrices exist. If there's only 1 degree 0 thing, and I only consider the product with itself, that's a 1 by 1 matrix. Nice. So I'm going to pick as my, I'm going to pick a Weil group to be finite Sn, fine. I'm going to put an S5 in the middle, an Sk plus 1 on one side, and S2k on the right hand side. There's no reason for this. It's what works, and I'll show you how the element looks in a moment. So that shouldn't make any sense just yet. So I'm going to pick the longest word. So lambda is going to be the longest word in this parabolic. So okay, let's do k 0. So this is the, oh okay, well, it's not quite the longest word in that parabolic. It's S1 times S4 in there. So that's the longest word in S4. That's the guy that swaps 2 and 3 and 1 and 4. That's just a strand by itself. And now I'm going to let k be bigger than 0. Oh, no, actually, that should be an S4 there. Oh, actually, okay. Anyway, we'll see what it is in a second. Forget the parabolic. So I'm going to stick. So that's S5. So that is now an L. I'll just do the next one. Okay, so what am I drawing? I'm drawing an element where I bring 1 strand in from the right each time, and 2 strands in from the left. So the base case is a little, you can't quite see the picture, but so what I did was I pulled in strand from the left and the right, and in some sense I'm counting this twice because I'm sort of saying that's not on the parabolic, but you'll see it in a sec. So the next one, I add 2 green strands on the right, 1 on the left. 2 green strands on the right, 1 on the left. 2 green strands on the right, 1 on the left. And notice that this is the longest word in S 1, 2, 3, 4, 5, 6, 7, 8. Because I've just done 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. This is the longest word in this copy of Sk plus 1 here. So Sk plus 1, S2k, longest words. Oh, actually, I didn't do anything wrong. I just misunderstood my slide. So this is going to be my lambda. And you shouldn't understand why yet, because I haven't shown you mu. But do we understand what this element is? It's just this guy where I just keep bringing 2 things at a time from the right and 1 thing at a time from the left.
And so you didn't get S4 in the middle.
This is an S4, yes.
S5.
Yes, that should be S4. Okay. Now, what is mu? So mu for k is 0 is this guy here. And notice that so what I'm going to do to get my degree is that I'm going to have that this is going to be +1 and that's -1. I'm going to cancel out degree 0. That's not quite, we're not there yet. But this is my element mu k for mu is 0. For mu is 1, I'm going to stick in something else. So I'm going to stick in some extra things. I've separated out those first bits. Like so, and what I've stuck in is the blue-green element from the previous slide, but with some black and some red crossings stuck in. And I'm just going to stick the same one in over and over again, basically. So I'm now going to stick in the green element from the previous slide, the blue element from the previous slide, and that same combination of black, 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 triple red, black, 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 triple red. And notice that the number of blacks and the number of reds is the same. And I'm going to do again, and this is just what you do, you just repeat. You're taking lambda, which is the green and blue bits, and you're sticking in some blacks and reds, and with the same number of blacks as reds, they're going to cancel out in a moment. But you can see how this element looks a bit like lambda k. That's what we're trying to do. We're trying to find an element lambda k that I can pair with one called mu k, which is this guy, to get what I want, and I also want to be able to do it inductively, which is why this guy here, the blacks and the reds, are the same every time. I picked it so I could do it inductively, and that's somehow the trick. Can you go back to lambda k for a second? So this one, I managed to get k longer here because I had more fewer things to draw. So remember, this is just the longest word drawn in a particular fashion. And okay, here, remember, I've basically repeated, well, what I've repeated is the new stuff I've stuck in to the old word. Plane. There is a unique path of degree 0 of shape lambda k and weight mu k.
Wait, why is it four crossings at the bottom, or red crossings at the bottom?
So there are 3 red crossings at each point that I stick in. But remember, I started with a guy. I started with this one, and I'm sticking stuff in the middle. So that guy stays the same. I stick something in. I stick the same thing in-ish. I stick the same thing in. So that those green ones are from K0. So I've stuck these things in, and I claim that there is a unique path of degree 0 of this shape and this weight for any k, which is what I wanted to construct, right? So sure, I haven't told you why it's true, but you can see where I'm heading. And how does it work? So I need this is mu k. I'm trying to get to lambda k. And I'm trying to do it by, and what is lambda k? Lambda k is the one where I delete all black and red crossings. So my argument for why this is going to have a unique thing of degree 0, because I'm going to just delete all black and red crossings. How am I going to do it? Well, I want to get the longest green word here, don't I? I want to look at a subword where it's the longest word. So if I need all the greens to survive, so lambda k has exactly the same number of green crossings as mu k. So I'm not allowed to delete any green crossing. That tells me that in order to get this to fold up to be the longest green word, I must delete every single occurrence of the black crossings. So they're all going to contribute a spot of degree 1. And on the blue side, exactly the same. I have to cross out all the black crossings, and they're all going to give me a positive degree count. And because of that, all the reds have to be minuses, because if this is plus 3 plus 3 plus 3k, plus 1 plus 1. The only way to get something of degree 0 is therefore to make sure that all the reds are minus the degree, right? In order for them to cancel out. And if I do that, it's going to look a little something like this. So let's do k as 1. So first, draw the word lambda k, which is mu k, this little region. And because I am not going to undo, I'm just going to do the lambdas. So they're all contributing strands. It'll make sense in a moment. So now let's do the black ones. And so actually for here, because these need to actually be different colors in the future, so I need black and gray. But all of these black ones, or almost black ones, I said they were all going to have to be, all going to have to not happen, right? So they don't happen. So that's why it's a spot, because at the top this didn't happen. Otherwise, I can't fold it up to the right place because I need to do all the greens and get the right word. So now that's all the spots. Now, because I did all those spots, okay, fine. The blues and the greens, you just do them all. That was the point. Now, I've not done any blacks. I've done all the blues and greens, and now I need to bounce all the reds. And whoo, there's a big braid. Fine, braids aren't important. But what the relations tell you is that braids don't matter in bilinear forms. But fine, they're there for now. We'll talk about them tomorrow. But let's just go back a bit. So spots for the blacks, forks for the reds, and their variants. So notice that I've added a little bit of color here so that you can tell. So here, I think that this is the reddish parabolic, by which I mean, and I couldn't draw this, so I just gave in. So I'm going to draw this one to be red, this one to be pink, this to be orange, which are all variants on the red family, but I want to be able to distinguish them in this diagram. So red, pink, orange, red, pink, orange, red, black, gray. So I needed to somehow add a little distinction between red and other red here. But you can see that what I've done is spots for the blacks and variants on black, forks for the things that are reddish, and then I've drawn the unique, well, not unique, I've drawn a braid, which allows me to do this down step at the right point because I need that the color is removable in order to get there. Okay. How is this? Is anyone finding this hard? Does anyone not understand what's going on? This is K is 1. It's gonna get simpler. So, okay, just to show you that your life gets better, because I don't care about the braid, I'm just gonna draw that picture in the future. I'm gonna say, okay, well, there's something going on here that I don't care about, but that's what the diagram will look like next time. But in the meantime, who doesn't get this, what we've been chatting about with this lambda K in UK?
I don't know what.
Cool. So what do you not get the words or do you not get the diagram?
You don't understand is like you're building you have a permutation in the box there,
Yeah.
and you're using the expression for that permutation to build the diagram.
Yeah, so I remember that, so this is the longest word, and I can fold this up by getting to the point where it's just blue and green, but I've got rid of all the blacks and reds. So this is mu K. Lambda K is obtained by deleting all of these blacks and reds.
Yeah.
And so at the bottom, I've got this word, and at the top, I've got the one where there's no blacks. Okay, well, apart from the initial few reds. Next, so here, black, black, grey, grey, red, orange, pink. At the top, it's just blue and green. Blue and green. And the bit that doesn't matter at the start.
I mean, I get that. I don't quite see how you filled in a diagram the way you did from that expression.
Cool. So, well, we've got time. We're doing so much better than yesterday. There it is. So, what is the element? What we're going to construct is, so we're going to need the longest word there, and we want lambda K to have, I'm going to use, so lambda K has a crossing here, and a crossing there in blue, green, but none of the blacks and reds. Okay, now so that's lambda 1. What is mu1? Mu1, well, I'm going to draw on the board, so that should be okay. So mu1 has the same start, but I want to get rid of all the blacks. I got rid of them. They've gone. I keep the blue and the green. Then I want to get rid of all the reds. Now, because of the direction of travel, the way I got rid of blacks was like, oh, I'm not going to do it. But with reds, I've got all the reds already, so the way that I don't do those is this way, right? So the way I don't do black is like this, the way I don't do red is like that, because all of these reds are removable, so there was no removable black to the right, to that direction. So I had to, so at this point, no blacks could be removed, so I couldn't do a fork, so I did spot. Okay, now I've just added the blue and the green so you can see them. Is the longest word for S4 not length 6? Did I do that wrong? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah, so there's 6 from. That showed some deference there that I was like, Jesus. So yeah, that's out of 6 because the longest word at the top there is the longest word S4, which is 6 terms. And I'm not going to do anything black because I can't, because if I did it, then I wouldn't be able to fold back up to lambda because it would get in the middle, right? There's going to be green and green here. If I did put grey green, I wouldn't be able to get rid of the grey. So it has to be a spot. Then do the blue and the green, they get all the way to the top, because if I didn't do any of them, it would be over. That would be the end of the game, because I'm trying to fold it up so it does have blue and green at the top, and I've got nothing to waste. There's no room for getting rid of blues and greens, because I can't build them back up. I've got the same number of blues and greens in lambda as I do in mu. Now, the last bit, you might think, oh, why don't you just do some red forks, or red spots, rather. But I can't do a red spot because at the point where I am in the Brouillard graph, I'm at the top of the Brouillard graph for S4. So I can't just start going up with reds. I have to go down with reds. And going down means doing forks. So there are the forks. And then that's just the wiggly braid in order to make it removable at that point. Okay. And obviously that's just very cluttered at the moment, and for aesthetic reasons, I'm just going to go.
That part is not. It's just
making some choice.
Yeah, exactly. You're just picking reduced words so that you can remove things. So it's not going to be important. Okay. And so this is the K is one case. I'm just going to draw the K is two case now. So, and this is what we're going to do tomorrow. We're going to take this diagram, we're going to put him below himself, and then we're going to calculate the coefficients alpha st, well, alpha ss, really, the same diagram quite, that appears. And when I take this guy, put his friend below him, match them up and simplify, I claim it's going to give me a Fibonacci number. And we know stuff about prime divisors of Fibonacci numbers, so that's going to be great. Okay, I'm all done. So, thanks.